Okay.
Thank you very much for the introduction. I'm very flattered of that part. To entertain Schilbach, I will talk about a kind of a different line of research. It's also kind of given the seminar title on the recurrent ETDS seminar. It's kind of mandatory to speak about recurrence problems. And so my talk about shrinking target problems and eventually always hitting points is kind of a research theme that tries to understand the recurrence behavior of typical orbits in a dynamical system. So let me kind of introduce the shrinking target problem, and don't worry about the number of slides. I don't plan to go through all of them. It's just to have some backup slides in case of questions. And yeah, please interrupt me at any point in case of questions or comments. And so I don't have a strict plan for this talk. What are shrinking target problems in dynamical systems? So the setting is very general, so we can look at a probability space and a measure preserving transformation. And then we take a sequence of subsets whose measure goes to zero with m going to infinity. And this kind of sequence of subsets will be called our sequence of shrinking targets. And such a sequence is called nested if the next one is contained in the former one. So you can kind of really imagine the situation as in the picture on my front page of the slides, namely that you have this sequence of shrinking balls centered at the same point, x0. And now we want to study the set of hitting infinitely often points. So the set is introduced like this. So if we have here our sequence of shrinking targets Bm, then we consider the set of points x for which for infinitely many times n, the nth iterate under our dynamical system T lies in the nth target set. Yeah? And we ask, with the set H infinitely often, we denote the collection of points whose orbit hits this target infinitely many times. And we can rewrite this set in set theoretic notation as a lim sup set. Yeah, because here we take this union to take into account that we want to look at those points that have a hit to the nth target. And here we have to take this intersection to make sure that we have infinitely many hits. Yeah, so by taking this intersection, we ensure that, for every m, there will be some hit afterwards. And so this is in set theoretic notation, this is a lim sup set. And so under the additional assumption that our sequence of targets is nested, recall that meant that the set Bm plus 1 is contained in the set Bm. Then this set of infinitely often hitting points is a T-invariant set. And we can prove this statement. So if we take a point x in H infinitely often, which by definition means that, for infinitely many n, we have that Tn of x lies in Bn. Then we can rewrite here the nth iterate in the way of saying, this is the n minus first iterate of Tx, which lies in Bn. But by our assumption that our sequence of targets is nested, the nth target Bn is contained in n minus first target. So we have for the point Tx that there are infinitely many instances such that the Tn minus first iterate lies in the n minus first target. So also our point Tx is a point in this set H infinitely often. So we have shown that H infinitely often is contained in the preimage of H infinitely often. So for the measure of this set, we have that it is less or equal than the measure of the preimage. But now, since our transformation T is measure preserving, this is the same as the measure of infinitely often. So we see that kind of the symmetric difference between the preimage and the set itself is a set of measure zero. So our set of infinitely often hitting points is indeed a T invariant set. And now that, of course, gives rise to a kind of 0-1 law if we have an ergodic dynamical system. Because, yeah, for ergodic dynamical system, we know that every invariant set has either measure 0 or full measure 1. So under the assumption that our dynamical system is ergodic and we have a nested sequence of shrinking targets, we get this 0-1 law for the measure of hitting infinitely often points, namely that this set has either measure 0 or full measure 1. And now the shrinking target problem in dynamical system asks, under what conditions on the decay rate of the measures of these targets do we have that this hitting infinitely often points have measure 0 or full measure 1. And of course, kind of to understand the measure of a limb subset, one might recall the Borel-Cantelli lemma from probability theory, which says that, okay, if we have a sequence of events in a probability space and the sum of those the measures of those events converges, then the limb subset has measure 0. And in case that the sum of the measures of these events diverges, and under the additional assumption that these events are pairwise independent, then the limb subset has measure 1. So now if we try to apply this Borel-Cantelli lemma, this classical Borel-Cantelli lemma from probability theory, in our dynamical setting of the shrinking target problem, we would take as the event En, we would take the nth preimage of our nth target Bn. And then kind of by measure preservation, we know that then the measure of En is the same as the measure of Bn. So the first part of the Borel-Cantelli lemma would tell us that, okay, if the sum of the measures of our targets converges, then the limb subset En has measure 0, which in our case translates into the, if we take here the limb subset of our nth preimage of the Bn, which was here our event En, then we get that the measure of the infinitely often hitting points is measure 0. So for that direction, we can apply the Borel-Cantelli lemma directly. The problem is for the other direction, because there the classical Borel-Cantelli lemma asks for pairwise independence, and that is certainly not fulfilled for our events here, because, okay, in the dynamical setting, it's of course exactly, we always look at iterates, so there is kind of an obvious dependence between those sets, and we kind of ask, okay, can we still have this kind of nice analog or nice version of this Borel-Cantelli lemma in our dynamical setting? And that is then called a dynamical Borel-Cantelli lemma. Namely, we say that measure-preserving dynamical system T satisfies a dynamical Borel-Cantelli lemma for some family of nested sequences Bm. If we get this dichotomy condition, namely that the set of infinitely often hitting points has measure 1 if the sum of the measures diverges, and that the set of infinitely often hitting points is a null set if the sum of the measures of the targets converges. So basically, if we have a form of our Borel-Cantelli lemma, of the classical Borel-Cantelli lemma, for our sequence of shrinking targets in this dynamical system. And as I drew this figure in the beginning, kind of typically one, as this family of nested targets, we look at a sequence of balls centered at the same, at a fixed center x tilde, and let the radii shrink to 0. And if a dynamical system has a dynamical Borel-Cantelli lemma for all sequences of balls centered at a fixed point, then we say that this dynamical system has a monotone shrinking target property. And this dynamical Borel-Cantelli lemmas have been studied in many dynamical systems, and I listed here a couple of results. I'm sorry. I mean, there is a lot of research on this dynamical Borel-Cantelli lemma, so I certainly have omitted a lot of interesting work here, but I just wanted to list a couple of ones. Maybe to start with, I mean, kind of Walter Philipp, he proved dynamical Borel-Cantelli lemmas for interval maps. And then, we see that this has been extended to other types of dynamical systems afterwards. And of course, maybe let me highlight here the work by Kleinberg and Margulis, who proved kind of dynamical Borel-Cantelli lemmas for geodesic flow on some homogeneous spaces. So let me emphasize this work because that had kind of important applications to geometry and number theory. Basically, it gave a new proof of the Khinchin-Gorshev theorem in simultaneous Diophantine approximation. So we see that this kind of study of dynamical shrinking target properties has a lot of applications, especially in Diophantine approximation. And of course, it's always good to mention that Margulis has worked in some research area that also gives a lot of significance or meaning to that area of research. So, of course, the general idea here is to use the mixing property of a dynamical system as a replacement for the independence. I mean, as I said, in the Borel-Cantelli lemma from probability theory, we kind of required the pairwise independence of the events, and that is certainly an issue in the dynamical system setup. So then the goal or the attempt is to use kind of strong mixing properties of the dynamical system as a replacement of that independence. But just mixing is not good enough. So there is a counterexample by Bassam Fayyad, who constructed a mixing diffeomorphism without the monotone shrinking target property. So kind of, we will see later that we will require some kind of speed of mixing, and this is usually then stated or phrased with a kind of decay of correlation estimates, and we will see that in a moment. So this is kind of let me call it the classical shrinking target problem in dynamical systems. And today I want to present or talk about a variant of this classical shrinking target problem, namely the study of so-called eventually always hitting points. This is in some sense a strengthening of our hitting infinitely many times. Namely, okay, how are these eventually always hitting points defined? The terminology was coined by Kalmer somewhat recently, although the kind of the problems have been around for some time before. Okay, so again, we have here a sequence of targets BM, and now we call a point eventually always hitting if there is a time n that could depend on that point x, such that after that time n, we always have a hit to our mth target in our orbit segment of length m. Yeah, so one more time. So a point is eventually always hitting if there is some moment in time such that afterwards the orbit of that point of length m always has at least one hit in the mth target. So and kind of this eventually always hitting then refers to the fact that, okay, eventually, so after some moment of time, your orbit always hits the m's target. Not necessarily that the m's iterate lies always in the m's target, because that would certainly be not, or just be true for a set of measure zero, because we have this, that our set BM are shrinking, but kind of that this orbit segment of length m always has a hit to our mth target. And yeah, one can compare the situation between the hitting infinitely often points and this eventually always hitting points also with the situation in Diophantine approximation. Namely, if we look at the Dirichlet's theorem, which says that, okay, for any alpha, for any m, there exists some iterate q, kind of some integer q between 1 and m, such that if we look at the distance between q alpha minus p, that this is less than 1 over m. Yeah? While the maybe more famous Dirichlet's corollary that is often quoted says that, okay, for any alpha, there exists infinitely many q, such that q alpha minus p is less than 1 over q. Yeah. So here, this Dirichlet's corollary really refers to this kind of hitting infinitely often. Yeah, namely that, okay, we have infinitely many instances where the iterate q alpha is 1 over q close, while then the situation of Dirichlet's theorem refers to eventually always hitting. Namely, here we say that, okay, for any m, there always exists an iterate between 1 and m, such that our iterate q alpha minus p is less than 1 over m. Yeah? So kind of, and in Diophantine approximation, this first instance is usually referred to as uniform Diophantine approximation, and the second one as asymptotic Diophantine approximation. But kind of in our language of hitting infinitely often, the second version would refer to our classical shrinking target problem of hitting infinitely often points, while the first one here would refer to our eventually always hitting points. And now kind of we can start this study as we did for the hitting infinitely often points, and maybe start by rewriting this set of eventually always hitting points in set theoretic notation. And we kind of see that this already becomes a somewhat more complicated set. So again, here I repeated the definition of eventually always hitting points, which was that, okay, there exists a moment of time such that then afterwards our orbit of length m always had a hit to the mth target. So this that we here look at the whole orbit segment of length m, that is written here as a union over the pre-images of our m's target Bm. Now we look at the first m iterations of T and look at those points that, which would lie in the m's target under the iteration Tk. So this would be this, the union refers here that we take this orbit segment, and then we want to have that there exists a moment of time, so that refers to this union here, such that after that instance n, we have that for all m, we have this hit. So, and this, that after this moment n, this holds for all m, this is stated or described here by taking this intersection now. So this that theoretic notation, we see that this set of eventually always hitting points actually becomes a lim-inf set over this union here. So now there's a situation to kind of want to ask the same questions as we did for the hitting infinitely often points, namely, okay, can we again kind of describe, okay, what are decay rates such that eventually always hitting points are a null set or a set of full measure. And for that, we can kind of go in parallel to the steps that we did for hitting infinitely often points and kind of see, okay, are these eventually always hitting points, are they an invariant set, for instance? So maybe one observation in the beginning. So if I define, as I said, lambda here, the union over the pre-images over the intersection of the targets, then this set lambda is a null set because kind of assume that we have a sequence of shrinking targets. So the measure of the targets Bm goes to 0. So here in this intersection, this intersection here will be a null set. And then, yeah, we take the pre-image of a null set. So this is still a null set. So if we ignore this null set, then kind of my introduction of this set of saying that we are studying a strengthening of hitting infinitely often points is true. Namely, if we look at the points eventually always hitting, without those points that kind of lie in the intersection of the targets, then those points are infinitely often hitting points. So kind of, okay, what does this, what I wrote here, what does this mean is kind of, okay, how can a point be eventually always hitting? Of course, you could have the situation that you hit the center of your target once, and then this hit would be in your orbit segment all the time, all the future times. So in that sense, maybe you just hit that target, the center of the target once, but then you do not have to come back at all in theory, and you would still be an eventually always hitting point. But apart from those instances where we kind of hit the center of the target once, the fact that we are eventually always hitting would require us to return infinitely often to the, or to kind of hit the target or a sequence of targets infinitely often. So kind of up to this null set of points which kind of hit the center of the target once, we have that the eventually always hitting points are contained in the set of infinitely often hitting points. So kind of you can imagine this for the point to be eventually always hitting, you have kind of heuristically speaking two ways to be eventually always hitting. You could either have a very close hit to your to the center of your target. So then you can wait a long time till you're required to come back, because this very close hit will serve here for many future targets until our targets become so small that you need a new hit. And okay, so then you will need another possibly close, very close hit, and then you can wait again till you need the next one. Or the other way how you can be eventually always hitting point is kind of that you have somewhat frequent hits to your sequence of shrinking targets. Okay, so then kind of by the same proof as I showed you for the infinitely often hitting points, you can show that this set of eventually always hitting points is an invariant, a T-invariant set. And so for ergodic transformations, we again have a 0-1 law for the measure of eventually always hitting points. So we can state now this kind of new shrinking target problem, namely under what conditions on the decay rates of our measures do we have that the eventually always hitting points have measure 0 or full measure 1. So let me show you kind of the first results that we got on this problem, and let me start with kind of sufficient conditions here, and which work kind of for very broad classes of dynamical systems. So for that, I need the notion of the first hitting time to a set E. This would be the first instance in time, the first moment in time, such that your iterate Ti of x lies in the set E. And then one kind of looks at this, at the lim sup of the measure of those points, such that the hitting time to the mth target, rescaled by the measure of the mth target, is at most T. So why do we take this rescaling? This is basically by Abramov's formula. You kind of you know that or basically it's Kach-Schlemmer in ergodic theory would say that okay, if I have a set Bm, then what is the expected hitting time? That would be 1 over the measure of your of the target. So and now basically, to take into account for that, we rescale and multiply by the measure of that target. And yeah, this would be kind of then the hitting time statistics. And our result says that, okay, under the general assumption that we have an ergodic system and a nested sequence of targets, and our hitting time function here is bounded away from, or is less than 1 for all times t, then we see that for all sequences of shrinking targets whose measure is bounded by a constant over m, then this eventually always hitting point has measure 0. In particular, we see really that this is shows a very different behavior from the hitting infinitely often times, because okay, if I have a sequence of shrinking targets whose measure is constant over m, the sum of those measures is divergent. So we know that by the dynamical Borel-Cantelli lemmas that the set of hitting infinitely often would have full measure 1. But for the eventually always hitting points, we get measure 0. So, and in that sense, we really see that there is a drastically different behavior between eventually always hitting points and infinitely often hitting. And yeah, this kind of our assumption here are in particular satisfied for systems having kind of hitting time statistics, which is often kind of an exponential distribution function, which has been proven for various types of dynamical systems. So this was our kind of the first sufficient condition to see, okay, under what decay rate do we get that the set of eventually always hitting points has measure 0. in the other direction to kind of state something, some sufficient condition for the set of eventually always hitting points to have full measure one. Kind of this now uses these concepts of the speed of mixing that I mentioned earlier. And as I said, those are usually stated or phrased in terminology of decay of correlation requirements. And for that, I recalled here the definitions of the L1 norm of an observable F and the bounded variation norm of observable F. And then we say that correlations decay with the speed theta for bounded variation against L1 observables if we have this inequality here, namely that if we look here at the correlation between G and F composed with our dynamics, that those correlations compared to the product of the integrals of the observables, that those goes to zero, basically with the speed theta n. And yeah, kind of this is a statement of kind of a speed of mixing for our dynamical system. And then, yeah, kind of dependent on this decay rate, we get different conditions for, okay, how can we guarantee that the set of eventually always hitting points is a set of full measure one. And yeah, don't bother right now about the exact statements here, but it just kind of our results here related the kind of speed of the decay of correlation to the requirements on the decay rates of the measures, so that we could still guarantee that eventually always hitting points have a full measure one. And this kind of decay of correlation, or this has been known for various types of dynamical systems as well. So just to kind of summarize those first results, let me state the situation for the simple dynamical system of the doubling map. So where we look at the map 2x mod 1 on the unit interval with a Lebesgue measure mu. And if we have any kind of nested sequence of shrinking intervals with a fixed center, then our results say that, okay, if those intervals go with constant over m, then eventually always hitting points is a null set. While if the measure goes like log m to the power 2 over m, then it is a set of hitting eventually always is a set of full measure one. So you see there is quite some gap in our results for a lot of rates where we can't say anything. So at about the same time was a work by Kleinbock, Konstantulas, Richter, where they also studied this question of sufficient conditions for eventually always hitting points to be a set of measure 0 or measure 1. And kind of in their setting, kind of they got tighter results, but for more restricted sequence of targets. So to state their results, let me state it as a kind of as a Bernoulli shift. And as they kind of had to look at nice target sets, which were kind of cylinders, where you look into your shift space, and the cylinders are those where your first coordinates are all 0. And then you see here they got a kind of tight condition, namely if those measures of targets go like 2 times log m over m, then it is hitting eventually always is a set of measure 0, while if it goes with here some d larger than 2, then hitting eventually always is a set of full measure. But this still doesn't give you a dichotomy condition because you could have sequences that fluctuate in measure, and kind of you're also wondering about, okay, what is now here kind of for higher order terms, so to speak. So the goal was, or the question was kind of, okay, can dichotomy condition? So it's like for the dynamical Borel-Cantelli lemma, where basically the sum of the measures of the targets gave, whether that one diverges or converges, gave you the decision whether hitting infinitely often was a set of measure 0 or full measure 1. And similarly, we wanted to find a kind of dichotomy criterion such that just looking at some kind of series, we could conclude whether hitting eventually always is full measure 1 or zero measure. And the main, or one problem in the beginning was, okay, how could this condition look like? And for that, it proved useful to kind of rewrite this problem of eventually always hitting points in a kind of statistical terminology. So for that, we look at a observable psi, which is a decreasing continuous function with a kind of singularity at 0. Yeah, so for instance, you could think of 1 over y or negative logarithm of y. Then kind of we fix a point x tilde that will, in our shrinking target problems, will be basically the center of our shrinking targets. And then we define the observable phi as taking the distance from a point x to this fixed center x tilde, and then map it under this function psi. And then we consider the stationary stochastic processes defined by looking at the observations along the iterates of our dynamical system, T. And for this stochastic process, we take then the maximum process defined as a maximum over our first n observations. Then this set of point x, such that the iterate Tn of x lies in our target or in the ball around the center x tilde with radius Rn, corresponds to the event that xn is larger than un, where this level un is the value of psi of Rn. Well, because, as I said, kind of, if you are, because here with the phi, we are measuring the distance from x to x tilde. So if you are in the ball with the center x tilde of radius Rn, so here our distance is at most Rn. So here kind of our observation would be larger than un, which was psi of Rn. And the event that the maximum process is at most un is then the event that, okay, for the first n observations xk, we have a value at most un. So after this kind of work, we can kind of phrase our set of eventually always hitting points, which in set theoretic notation was this set here. We can now rephrase that in statistical terminology. Namely, okay, here this, as we wrote here, to be of this form would correspond to that our xk is larger than um. And okay, we still have this union. So now if we are in this union, that would mean that among our maximum process, the maximum process also has to be larger than um. So there has to be at least one moment in time one k between 1 and m, where xk is larger than um. So the maximum over the first m observation is larger than um. So we lie in this set here eventually. So that in statistical terminology, to be in this lim-inf set means that eventually the maximum process is larger than um. So we are in the frame, we have kind of rephrased our problem of eventually always hitting points in a statistical language, and it's kind of the language of statistical extreme value theory. So let me give you a bit of a insight or overview of extreme value theory in dynamical systems, which kind of, yeah, is in that setting of that we have a stationary stochastic process xi, and we look at its associated maximum process. And then extreme value theory is based on understanding the limiting behavior of the maximum process, either almost surely or in distribution. So when you study this maximum process in distribution, then you usually want to find rescaling sequences an and bn such that the measure of the set of points such that an times the maximum process minus bn is at most u goes to some non-degenerate distribution function g of u. The second aspect of study are so-called almost sure growth rates for a maximum process, where you try to find optimal bounding sequences such that almost surely after some moment n, your maximum process is bounded between Vn and Un. Yeah? So in other words, kind of you look for those bounding sequences Un and Vn such that the set of points x such that the maximum process eventually lies between Vn and Un, that this set has full measure. And kind of, maybe let me skip, or let me briefly go over this as well. So if we are in our setting of this maximum process, then we say that a maximum process has an extreme value law if there is a non-degenerate distribution function such that there is, if we have for this kind of sequence of levels un, such that then the measure of the points where the maximum process is bounded by this level un, that this goes to 1 minus h of t. So this kind of extreme value law can be motivated by the IID case. So if we ask about, okay, that the maximum process is at most un, means that, okay, and we are in the IID case, then this measure would basically be that, okay, we have to go look at the complement. No, so that all times we have to be at most un. So to measure that, I look at the measure of that would be 1 minus the measure of being larger than un. Since this, in the IID case, we need this for all our first n observation, gives us that we have to raise this to the power n. And now I kind of just rewrite this as n times measure x1 larger than un, and then I divide by n. So just get here our value t, and then what I end up here would be exactly that this goes to e to the negative tau. So this would be an example of such an extreme value law. So extreme value theory itself kind of has a lot of applications. And yeah, for instance, one example always refers to the kind of issue of flooding. And so here in this picture is kind of is a picture of the Netherlands, and for the Netherlands, a large proportion is actually below the sea level. So yeah, it's about 40% of the Netherlands is below sea level. The Dutch government has decided that the probability of a flood in a given year should be bounded by some threshold here. So now they ask, how high should the dikes be? So kind of the issue becomes you want to study the probability for events that are more extreme than anything that you have observed before. So usually in probability and statistics, you look at how many times have an event occurred, and that gives you the probability for that event. But now you ask about kind of extreme events that are more extreme than anything that you have observed before. So if you follow that old approach of looking at, I take the number of occurrences divided by a number of measurements, then this would just give you probability zero. So extreme value theory is a branch of statistics dealing with the extreme deviations from the median of probability distribution. It seeks to access from a given ordered sample of a given random variable the probability of events that are more extreme than any previously observed. So, and this, of course, has a wide range of application in the study of extreme or rare events, and often tied in with risk assessment. And now here in our we here want to study the kind of almost sure growth rates of this maximum process, and from that kind of then get conditions on the decay rates of our measures to conclude whether eventually always hitting points as measure 0 or full measure 1. So we study the almost sure growth rates for the maximum process and want to determine these optimal bounding sequences such that our maximum process eventually lies between these sequences Vn and Un. Yeah, and as I said, hereby we want to find a dichotomy condition for our set of eventually always hitting points, which, as we deduced earlier, could be rewritten as this, that the maximum process eventually is larger than where referred to the value of the under our observable psi of the radii sequence Rn. So, and this kind of rewriting or put it in this statistical framework was very helpful for us because it gave us the idea how should this condition on the dichotomy condition look like. Namely, in extreme value theory, there is a result by class, and it is called the Robin-Zsigmond series condition. Maybe for the situation that we have an IID process, so probability measure P, and UN is a non-decreasing sequence, and this requirement here, then we get this kind of dichotomy condition. Namely, if this sum here converges, then the measure of the maximum process eventually is larger than UN is 1, while if the series here diverges, then this event has probability 0. So this kind of Robin-Zsigmond series criterion, it gives us a dichotomy condition to understand this eventually always behavior of the maximum process Mn. And we can kind of apply that, or we could now, if we want to see or want to apply that in our dynamical system setting, we keep in mind that, okay, the probability of our observation being larger than UN corresponded to the measure of the ball with a radius Rn around our fixed center x tilde. And the probability of the maximum process eventually being larger than UN, to the measure of eventually always hitting points. So kind of we will now on the next slide kind of see how, or the kind of see the version of this Robin-Zygmund series criterion in the dynamical systems setup. Here again, for that result, there is a problem that this is for ID processes, so it doesn't work for the dynamical system setting. So we had to kind of again work with decay of correlation estimates and so on to try to find the dynamical systems analog of this Robin-Zygmund series criteria. And this is in joint work with Mark Holland, Maxim Kirsebom, and Tomas Persson, where we could kind of show this Robin-Zygmund series criterion in the setting of piecewise expanding interval maps with an ergodic measure, which is absolutely continuous with respect to Lebesgue. And then kind of, yeah, if we rewrite our eventually always hitting problem with these observables, as we did on the earlier slides, then we get exactly this dichotomy condition, namely that, okay, for almost every center X tilde, we have the following dichotomy. If the sequence of radii satisfies that this series converges, then eventually always hitting points has measure 1. If the sequence satisfies that this series diverges, then eventually always hitting points is a set of measure 0. So we kind of have that a version of this Robin-Zygmund series criterion in the dynamical system setting. And it's kind of interesting that, okay, well, as for the classical dynamical Borel-Cantelli lemmas, if you recall that slide was where I had all these examples, kind of the first one that I stated there was also for kind of interval maps. And similarly here, we also at the stage that, okay, we could verify that for those class of interval maps. And now, of course, it's an interesting question, okay, to which extent can you generalize or can you extend this to other type of dynamical systems? Let me maybe end with one application of this result in number theory. Namely, we can apply our result to the Gauss map stated here. And the Gauss map admits an ergodic measure with an invariant density, it's a so-called Gauss measure. And then if we take as the observable the integer part of 1 over x, and we look at the sequence of shrinking targets at the center x0, then kind of the observations that we get along our iterations of the Gauss map would be the kind of coefficients of the continued fraction expansion of a number x. Yeah, so recall that for a number x, that can be written as its continuous fraction is usually denoted in this way here, where kind of these coefficients here come from this continued fraction expansion. And kind of now, if you look at that, the Gauss map always takes 1 over x. So basically with each iteration, you pick up that coefficient ak. So the under our observable here, you see exactly the coefficients of the continued fraction expansion of that number. So now our result kind of gives us a statement on the growth rate of this of the maximum of this coefficients, namely that if you kind of scale by log n over n, that then it goes with 1 over log 2. And so this type of result was already contained in that paper by Walter Philipp. But now, since we get this dichotomy condition, we can get to finer scales and could really kind of describe the, yeah, exactly describe the growth rates of a typical real number x. Okay, maybe this is a point to stop this presentation.
Oh, okay. So thank you, Philip, for this wonderful presentation. I mean, I really enjoyed the talk, and it's quite. I didn't know about this sequence of work. Like I've
No,
looked at it.
I promise I wanted to entertain you with something new.
No, this is indeed entertaining. So first, I will open the floor up to the audience if you have. So maybe I'll stop the
Hmm.
recording at this point of time.